Okay, first of all, I would like to thank you everybody on watching this presentation. Today I'm going to present our publication in JCISE on segmentation-based wireframe generation for parametric modeling of human body shapes. The co-authors are Dr. Jida Huang, who is an assistant professor at University of Illinois at Chicago, and I'm the presenter. My name is Tsz Ho Kwok. I'm from Concordia University from Canada. And this work is actually a part of the whole, like a larger project. And thus, today I will also present a little bit more from the background. So the outline is I will give you a very brief introduction on how it comes to this particular work, and then talk about the segmentation-based wireframe generation and characterization method, results, some design guidelines we will propose that at the end, and we conclude. So first of all, parametric human modeling is actually very useful and important in the field. Parametric human body modeling is like using the parameters. Changing the parameters, you can generate different model very quickly for an automated procedures. Based on that, meaning that you can generate different human body shape with just a set of parameters, and you have a lot of applications, including the garment design, garment animation, medical applications also. This is a very important domain. And obviously, in parametric human modeling, the first important part is about the learning. Learning the variation, learning this body change, learning the shape, all those things. And in learning these data, we can use machine learning. However, machine learning, like neural networks, are mostly black boxes, meaning that it will create the predictive models directly from the data, which humans may not really understand what is it. Like we set up the number of layers, number of hidden layers, and number of hidden nodes, and we try our best to change it to achieve this accuracy by trial and error. But sometimes like, oh, why does it work for 10 hidden nodes, but why doesn't it work when I use 11 hidden nodes? We don't really know why. And then the problem is it also commonly suffer from overfitting, particularly when you're dealing with high dimensional data with few samples. And this problem is very important in human body. For example, like if we have a human body database, each human body, you can be represented by 10,000 or even 100,000 of vertices, but we may only have like 100 to thousands of human body in the database. For that, then this overfitting problem is significant. So the question is, how can we improve it? How can we improve this training, this learning performance on a human body database? And the idea is we want to incorporate certain this interpretable meaning into the training, into the neural network. And to do so, one of our previous work is talking about using the wireframe. What is wireframe? Wireframe is talking about the lines, a set of lines on the human body, like this line, this line. They normally divided by like a girth, hip girth, or wrist girth, this kind of dimension to define them and then separate into different match patches. And we use this wireframe as an intermediate layer on the neural network to link between the semantic parameters and the mesh underneath. So meaning that we still use machine learning, this kind of, because the capability of learning some relationship that we don't know is very strong, but we also incorporate this kind of semantic meaning or this interpretable layers into the network so that it can guide the learning in between. So it's kind of a crossover between different methods. And because of that, separating the wireframe, separating the learning into subproblems, it will be much faster compared to US learning as a whole. And it can also reduce errors. In this chart, you can see from the synthetic errors, this new method, generally speaking, have much lower and more stable result compared to the other method that you can see here. This is an error, the larger the worse. So from here, then let's come to the questions to this particular work is, The current wireframe definition method is mainly based on this anthropological experience of expert, meaning that you need to define it manually. Otherwise, it may not be very meaningful when you join something. But then, is it really good enough? Or a particular question is, can we have a better wireframe wireframe to be automatically generated? And can this process can be automated? So that is basic question to motivate our work here. And we have some observation. From the wireframe, you see that the wireframe here separating into these different mesh patches. If we observe that wireframe is a set of coastal curves deriving the human body into small mesh patches. And by looking at it in this way, we trigger us to think about, oh, there are some other technology having similar features, which is the mesh segmentation, which decompose a mesh into meaningful subparts. And because of that, we are thinking like, there are certain different similarity over there. Can we cross over them and then try to see if we can, by doing so, mesh segmentation have been done for so many years, have been well developed. Can we cross over them to create something generalized and using mesh segmentation to help this wireframe generation and create a automated and particularly for improving the learning performance. Thus, we propose this new framework called the segmentation-based wireframe generation. We start with a human model and we apply the mesh segmentation. And when a human shape is segmented into different partitions, the boundary between them, we can serve as the wireframe. And then we can create this kind of lines as a wireframe for the purpose. I want to mention this, although this only one model is shown here, but it is for the whole database of the human bodies. Because in the database, there is a bijective mapping, meaning that there is common connectivity between the models so that the result can be shared among the models. And with this, one problem you can already see here is the segmentation result is really based on the mesh quality. So you may have zigzag or non-smooth curves between them that may not be desirable. So we want to smooth them out. So what we apply is also apply the boundary smoothing operation to smooth out the boundary so that they will be smooth, they will be straight on the surface. So the movement is along the original surface, so it won't change the shape of the model, but it will strengthen out the wireframe. Now, this is good. I mean, using segmentation, we can automatically obtain different wireframe, but the problem right now is different segmentation approach will lead to totally different wireframes. And each of them are using different segmentation principles. How do these segmentation principles affect the learning performance, affect the parametric modeling? That is the major question, the major research question we want to answer in this work. And the methodology we're using is, first we'll make hypotheses based on from the knowledge of statistical learning that we commonly know. And then we will select different segmentation approach with totally different properties and then test the hypothesis based on that. From that, then we can draw certain conclusions, draw some from the result, then we can create some design principle or guidelines for that. So we have 4 different hypotheses, or we call the criteria as well. And I want to present it quickly one by one to mention them. The first one is based on the knowledge that we know when we're doing learning, we want the dimension of parameters and variables, or we call it, like in other words, it's called the input and output. I prefer it to be similar. The reason why is if there is a totally imbalance between the data, like one of them are very huge, one of them are very small, then the problem will become like either overdetermined or underdetermined. In that sense, we know, even not talking about machine learning, in just simple regression, we know that this kind of problem normally will create much more errors. So with this knowledge in mind, and we also have an observation in our case, we found that the parameters and variables in our case is actually the positions of the pawns or the vertices that we're talking about on the wireframe and the mesh patches. Then in this case, then we make our first hypothesis is the dimension ratio of the boundary wireframe and to the mesh patches should be better to be close to 1. That meaning that they have similar dimensions. With that, then maybe it will have a better performance. That is our first hypothesis. The second comes from the knowledge of statistical noises could disturb the learning process. And this is common. I mean, noises are always something we want to filter. We don't want them. Then we observe in our case, the generated wireframe could also contain irregular curves, even after the boundary smoothing. Because if the structural shape is different, then no matter how you smooth it, it doesn't help. And for example, if the clustering is like this, and then you finally get a wireframe like this, then it is totally irregular, and you can treat it as noise, like the statistical noise that we normally see. So we make our second hypothesis. If the segmentation give a smoother boundary wireframe, is beneficial or is better for the learning performance, will improve the learning performance. That is our second hypothesis. The third comes from the relationship, is the actual relationship between the parameters and the variables. If they have no relationship at all, no matter how you learn it, you won't learn anything meaningful. So if we establish or build up the setting of the parameters and the variables, they have deeper relationship, have stronger relationship, then they will have the trained model will be better. So observed in our case here is the boundary wireframe actually is serving as a handle to describe the patch, to describe the geometry, and to describe the shape inside. So meaning that if the wireframe is follow or having similar shape with the mesh patches, or have more description to the mesh patches, it may be better. So we make our third hypothesis is about the topology, or about the genus number. Normally we use genus number to describe the topology. What does it mean is we can also, in another way, is we count the number of coastal boundary wire curve. For example, on this link, for this mesh patch, this is one mesh patch, and you only have a wireframe or the line coastal curve here. Then we call this as the one coastal boundary wireframes, or genus number 1. And then for this one, we have 2 coastal boundary wireframe, we call it 2 genus number. Then our hypothesis is the larger the genus number of a mesh pad, the more effective in learning. In other words, you can see it here, it's like if there's only one wireframe here to describe, we want to use this one wireframe to describe the whole feet shape here, it's kind of difficult. We can already feel that. But if we're talking about using these two to describe the symmetrical surface with a little bit variance, most likely it will do a good job. So that basically is the idea. So we have this hypothesis saying that the higher genus number will give better learning performance. Finally, the fourth hypothesis is come from the knowledge that normally we want to sample the data, or we want to obtain the data as uniform and sparsely distributed as possible. So the data should be uniform distributed. And back into our problem here is if the mesh patches have significant different sizes, the learning result will be biased, meaning that if some of the parts have more vertices, some of the parts have less weight, then the learning result will be biased. Some parameters, when changing it, the errors could be different, and the effect could also be different. So we don't want that. So the fourth hypothesis that we make is the segmentation, if it is being more uniform, it will improve the overall quality of parametric modeling. So these are the 4 hypotheses. To summarize, the first one is about the number of points, the dimension ratio between the wireframe and the mesh patches. The second one is about the smoothness of the wireframe. The third one is about the topology. The fourth one is about the uniformity. And based on these 4 criteria, we also select different types of segmentation method to adjust this and to test this hypothesis. There are also 4 different segmentation methods are selected. The first one is the curvature-based. Curvature meaning that they group similar surface with similar curvature. Like if they are coming from the flat surface or symmetrical surface, they will group them together. And because of that, then they will group the same primitive features. Then you will result in kind of like compact topology as the end, so we can test for the topology criteria. Uniformity obviously is about the uniform of the segmentation, and then complexity is they will group them to make sure the patch or make sure the cluster is convex. And if for that case, you make sure the curves, the boundary will be smooth. Won't have a lot of concave arbitrary shape over there. And the last one is the consensus segmentation. It's more like it's not a particular segmentation principle. It's more like a higher level. The method it does over here is it will like oversample, make a lot of sampling, or over segmentation, make a lot of different segments on the models, and try to see what are the common ones that you can see. If those are more common ones from different segmentation method, then they will keep them. So the result will be more like a stable, proper-sized patches and looks more meaningful or more high-levelly reasonable cluster. So these are the 4 selected segmentation method, and this is an illustration using 15 segmentations patches. So this is talking about using the curvature to segment, and then this one is uniformity. This one is talking about complexity, and then this one talking about the consensus patches. And then you see each of them actually generate totally different patches and have totally different features. Now, then we quickly go into the results. So in the result, in the testing, what we use is we use a database. In the database, each human model contains 1100 vertices, and each vertex have 3 coordinates, x, y, z. So meaning that at this dimension is 30 something hundreds. And we picked the 8 semantic parameters, which are like the height, the bust curve, hip curve, those kind of semantic parameters. And a database of 77 subjects are used. 67 are used for the training, and 10 are used for the testing purpose. And to measure like the accuracy and the performance of it, the syntax error is used by comparing the distance between the corresponding vertex, meaning that after the learning, we use the same parameters as the input and synthesize a new human model. And this synthesized model, we also have the same model as a ground truth in the database. So we compare these 2 models, the synthesized one and the ground truth one, vertex by vertex, and then see what are the difference over there. And this will be used as an indicator, like how good or how bad of the learning performance. So for the first criteria is talking about the dimension ratio. This dimension ratio is, we mentioned, it's better to be closer to 1. So from this result, each point over here is actually 1 mesh patch. And because on the mesh patch have different number of vertices, so you will use the average point error. That means each vertex have 1 error, and we average it out, unify it, so that it can be comparable among different mesh patches, and using the average point error over here. And they use the 4 different segmentation methods are shown here, and they are all of them are plotted with the errors point shown in the table. From here, we can see 2 observations. The first thing is along this line, ratio 1 here, along this line for all of them here, we will see that there is a big change when these 2 lines. So most of the time, on the left of this line is having a lower error compared to on the right of this line. So in general, lower than 1, it will be having a lower error, meaning that we call, because we know that the input is the wireframe, and then the output is the mesh patches. And if this is lower than 1, then that means the wireframe is actually a little bit less of the dimension compared to the mesh patches. And it makes sense because the mesh patch is the handle, so it have a little bit less of the dimension. But if in case it's higher than 1, that means the wireframe is even more features than the mesh patches, then it actually is not making much sense. So this part lower than 1 have a little bit lower error is come from this way. The second observation is the symmetric trend. this is more like a symmetric along this one. From the left to the right, then you have a decreasing trend. And then further, after this one, you have an increasing trend. Then it means you really have a lower error when you get to the ratio like close to 1 here. So it actually agrees with the hypothesis that we made. Of course, there are some outliers, but when we plot the outliers out, then you see that these outliers are normally talking about there's a one wireframe describing the whole surface, like this one, that they actually have a large shape difference of the wireframe with the mesh patch. So from here, we can see the result actually agree with the hypothesis, but there are certain other outliers, meaning that this dimension ratio is not the only factor to be used to find an optimum wireframe generation method. The shape difference may also be taken into account as well. So then we go on to the second criteria, the smoothness. For measurement of the smoothness, we use the Gaussian curvature, and we average them out for the whole wireframe and plotted on the x-axis here. For this curvature, the smaller, meaning that it is smoother. So the smaller the value, the better in that sense. So from here, we have a very clear trend for this case. You can see that when it's getting smaller, the trend is also getting smaller. So the better quality from that. So which agrees with the hypothesis 2. When we have a smoother boundary wireframe, the dynamic performance is also improved. But you see the slope is not really deep. It's very small. The slope is very small. So meaning that it does matter, but it doesn't have a very, very significant effect on the learning performance. The third one is talking about the topology. It's talking about how many number of genus number or the number of boundary wireframe over there. And from this, we can see there is a clear improvement trend. So the errors is keeping decreasing with the increase of the number of boundary wireframe. And this trend is very clear in this case. And thus, it also agrees with our hypothesis saying that the larger the genus number, the better the learning performance. And we also can observe there's a big change, let's say from 1, 2 here, and there's a big change at 3. When you get to like a genus number of 3, it suddenly have a big decrease of the error for most cases over here. For this one, doesn't even have the segmentation doesn't even have a 1 or 2 here, so it's starting with 3. But for the other cases, you see that there is a big change starting from the genus number 3 and then getting to a plateau afterward. So roughly, we can see that we want to have a higher capacity, but at least like around 3 will be good. Finally, the fourth one about the uniformity. We use this equation to measure the uniformity. This is talking about the whole segmentation and using the standard deviation between different patches and divided by the mean of it. For this case, meaning that this value is smaller, the better. That means the smaller, the more uniform of the patches. And we also try to, because of that, we try to see how is the number of mesh patches will affect the uniformity. So we can also see a clear trend is that if the patches are small, there are more patches, the more uniform you could be. And it's around 30, 40, 50, this will get in the plateau over here. And since then, all these results are plotted. For this one, each point is for one segmentation, one model. And then the result are plotted against from the model error to the uniformity over here. And as mentioned, the smaller the better, the smaller the more uniform. And we can see also a very clear trend that decreasing of the error with the decreasing of this uniformity value. So again, it also agree with the hypothesis 4. And finally, we also want to compare with this 4 method with the previously manually defining method. And you can see like the model error for the previous manually defining is around 220, this set of level. For those using curvature is not really better. Using the complexity is similar. Using the consensus is also roughly similar. But funny, there's one funny observation is using the uniformity segmentation, you're actually getting a lower error compared to the using the semantic meaning definition of the wireframe. So we do find some method can produce a better error, but definitely it's not enough. We need a particular segmentation method to create a new way, particularly for learning performance. And there is also some observation is that the testing result in general agree with the hypothesis that we made, but the influence of each of them are different though. So that's why to facilitate further development of an automated wireframe generation method, so we develop certain guidelines ordered by the importance over there. The first one is more boundary from the hypothesis 3, the topology. This is also the most important one. It's more boundary wireframe per mesh patches will be better. That means the more complex of the topology of the wireframe will be better for the learning performance. That is the first one. The second one is if we don't have any knowledge about the shape, if we're not doing it with human body, doing it with other cases, we also want to learn them, then partition uniformly is good. Always giving a uniform distribution is better than the other cases. If we know that, then a different story like the first one. The third one is about the dimension ratio. It better to be having an interval around 0.8 to 1. This region will give you the best result. And the curve should be as smooth as possible, though it is not the most significant factor. It helps, but not the most significant factor. So these 4 design guidelines we make based on the knowledge we have in statistical learning, and then develop for the testing, and from the result, we got this conclusion. And to conclude, this presentation is we presented a segmentation-based wireframe generation for human body learning, and we made the hypothesis on the quantitative criteria for learning performance. We tested by various segmentation methods with totally different segmentation principles, and we developed this design guidelines for automated wireframe generation. The implication of it is in the future, if we can do that, of course, we can develop a particular method, segmentation method for wireframe generation. But we can also think as a machine learning community, we are also thinking about like using semantic meaning to define the intermediate layers of neural network. It helps a lot. And similar guidelines, we can also develop for data segmentation on other applications. And if we can in the future also like cross over this segmentation method on the data on other domains, we can do a learning driven, learning aware segmentation method. That would be fantastic. So at the end, I want to acknowledge, first of all, I want to thank you, the organizer, Dr. Krypto, for organizing it and also help me to presenting here. And I also want to thank you for your attendance, your reading, your watching of this video. And finally, I want to thank the funding agency from Canada, NSERC, to support the research. So thank you so much. And I will end here.